All right, so we're going to jump right in here. The title of my presentation was How to Speed Up the I2C Bus by 250% by Wednesday. But the question I should really be asking is, why on earth would you want to do that? And the general answer is that our customers who use our products want to go faster. They want to put more data through the existing system and not change it very much. And why are they doing that? The answer is, in their world, they need to service more slave devices on the same bus. So to get the same performance out of more devices, they need to speed everything up. And we want to take advantage of newer IC technology. Since the I2C Bus was invented, we have greatly improved our general technology, and therefore we can apply that to speed up the I2C Bus. So how would you speed up any bus? I think the answer is pretty obvious. We just increase the clock speed. You can do that, but there's some consequences, which is the bulk of my presentation today. You can also reduce the dead time that was built into the I2C spec. Without going too much into the history, the I2C spec has been around for 30 years. And during that time, we've made a tremendous advance in technology. Think back to the 1980s. When this bus was created, most digital signals were 5-volt logic. They were driven by TTL, and 10 nanoseconds was considered lightning fast. 100 nanoseconds was considered a more reasonable speed. Think forward to today's technology, and we can beat those numbers both in voltage and in speed. So what happens is, if you have a spec that had dead time to compensate for all the technology, if you reduce that dead time, you can get more throughput through the bus, so you can, in general, speed everything up. You can also increase the strength of the drivers. Think back to the 1980s technology. We started with 3 milliamp drivers. They were typically bipolar technology, and they were open collector bipolar transistor devices. Using FET technology, we can use a device that has a smaller area on the die and a much stronger drive. So we can increase it from 3 milliamps to currently 20 milliamps. Most of the parts from my employer are better than 20 milliamps, but the spec said you will need a 20 milliamp driver to go faster. And finally, and if you've designed with the I2C bus, you know about this, the way the bus operates, you choose the value of the pull-up resistor based on the capacitance of the hardware that you're employing. So that can be a challenge, because if you have a flexible product where you're going to expand it or allow your customer to add on to it, the choice of the pull-up resistors becomes an engineering challenge. If you make those resistors smaller because you have stronger drivers, you now have a smaller time constant on the bus, so you can move faster, you can meet the goal of producing more data in a given amount of time. Well, I think I'm getting ahead of myself here. We should go back and tell you what the I2C bus is. So this is a very simple explanation. I apologize if you're experts in I2C and you're going to find this a little dull and boring, but we'll run through it fairly quickly. If at any time I say something or imply something that you don't understand, just raise your hand and I will try and answer your question. There is a Q&A session at the end. So here's our I2C bus. And to make it work, we need to add at least 2 things to it. And by the way, I2C is a contraction of the phrase integrated circuit. Philips invented that in the 1980s. And the original purpose of this technology was very simple. They wanted to put microcontrollers inside television sets back in a time when television technology was analog. Typically, it was a cathode ray tube, and it was a mature commercial product, consumer product, and there wasn't a lot of fat on the bones to spend on high expensive technology. So what they were looking for was a very simple bus that could be added and that it could be done inexpensively. And that's how the I2C bus came into being. And the purpose is to link a slave device. In a television, it might be something simple like the control for volume or the control for channel change, to a brand new microcontroller, which is the new technology going into the device. So on one side of the master that controls the bus, we have a CPU. On the other side of the slave device that's connected to the bus, we have something There's something maybe nothing more than switches or LEDs. It may be a device that creates data, for example, a temperature sensor. Now, the bus is split into two different domains. The first one is the physical layer, which we'll talk about. And the second one is the protocol layer, which we'll talk about next. So the physical layer is just a name for the electrical connections, and it consists of two wires. Some of our competitors call it TWI for two-wire interface to get around the trademark of I2C. The two systems are interchangeable. They may be connected together. So our two wires carry clock and data, and they will only work if we have a ground connection and a power supply connection. So here's our data line. We call it SDA for serial data, and our clock line, we call that SCL for clock. We connect them to our master, which is very often a microcontroller, an SoC, system on a chip, FPGA, or some custom silicon that has I2C capability. And we connect it to a slave. And it's implied in this diagram that the VDD supply and the ground are connected together. It won't work unless you add two resistors. The resistors are necessary. If you forget to put them on your schematic, I'm not the only one in the room, I'm sure, that's done that. If you leave them off the schematic, the bus will not work. One of the things that's characteristic about the I2C bus is the devices pull the signal lines towards ground. At no time should you pull it high. So this diagram is not legal. We'll cross those out. In your mind, you should imagine a connection that is pulled to a positive supply with one resistor, and multiple places along that line you can pull it to ground with switches. Typically today they're FETs. Older technology, bipolar devices are still valid, and they may use bipolar transistors. When the bus was designed for a binary signal, we needed to decide what part of the supply range would be a logic 1 and what side should be a logic 0. Obviously there's a dead band in the middle on my barometer that's colored red, and the values we chose were 70% and above is a 1, 30% and below is a 0. In the early days, that was a 5-volt world. So those are the numbers you end up with for the threshold voltages, and obviously you want your bus to be in the green section for zeros and ones. Fast forward 10, 15 years from the original design, most people are moving to 3.3 volts, so we simply scaled the same percentages and got new values for voltages. What happens in the future? Future CPUs and similar devices that are in leading edge construction for semiconductor fabrication will probably run from 1-volt power supplies. They're very close now. Some of the Intel products that are in the marketplace are 1.25 volts. Some of them are indeed 1 volt or 1.05 volts. So to stay current with that technology, you need to take those 1-volt signals and step them up to something you can use, which is typically 3.3 volts. When you make the signals very small because you only have a 1-volt rail, you end up with a problem for system noise because your thresholds are so close to the ground and the supply. So for the hardware engineers in the audience, there's your challenge: how to make the same thing work at 1-volt power supply. If you look at the signal from an I2C device using a mixed signal oscilloscope, for example, you would expect to see a binary signal. But you have this thing that's not quite binary. I see a few people smiling in the audience. You've obviously looked at these signals, and you've noticed that we have 3 levels. It's still a binary signal, so let's just walk through them. The one at the top is obvious. That's logic 1, and that's well in the green zone. The one at the bottom, system ground or very close to it, is obviously logic 0. So what's this odd level halfway up the green bar? It turns out that the way the bus works, there may be an offset on the bus for the logic 0 condition. And this offset may be there as a consequence of wiring resistance, connector resistance, and the physical size of the bus. It may also be there because we deliberately put offset onto some of the parts. And some of you may already have come across that. You find that parts can, under certain conditions, be connected together without any restraint. And under different conditions, you simply can't connect the parts together because this offset voltage interferes with the way they work. So this offset means we have a 3-level signal, and it's caused by differences in strength for the drivers, the wiring, resistance of the connectors and PC board, and also by something called bus buffer offset, which is a deliberate case where we put a signal on top of the logic 0 for another reason, which we won't go into at the moment. This level is typically 400 millivolts or less if you're running from a 3.3 volt power supply. That's the secret of the hardware. Any questions up to this point? Okay. We'll switch gears. Protocol layer. Protocol just means how you format the data, how you move the traffic on the bus, and how you stop collisions if more than one device is trying to speak at the same time. So here we are with our basic diagram. We have a bus controller, and we have a slave device, and we have a wiring connecting 2 wires, 2 resistors. So that's the minimum system you have to have. Now today, very often the M in my diagram, the master, is built into a microcontroller. And if you're operating at a fairly high level in the design of the firmware, all you do is just send it commands. There's an I2C library that you compiled, and it takes care of formatting the signals that go out on the bus. You don't have to worry too much about it. So how does it transmit data on only 2 wires? Here is a sequence, and we're going to start on the left-hand side of the screen. And before we get to the yellow box, both the clock and the data line are high because the bus is idle, no one is using it, and the 2 resistors pull those lines towards the power supply. When data falls while clock is high, we have a unique condition that cannot happen any other time during the message, and we call that the start condition. Once we have a start condition, we can now put data onto the data line, and we can clock that data. The clock signal, SCL, originates in the master. At no time is the slave device allowed to generate the clock. So in the example given, when the clock went from low to high into the green section, whatever data was on the data line is taken as valid and is then read into the slave device if it's transmitting, or read into the master if it's pulling data from the slave back towards the master. So we do that for the next bit. We keep doing that until we run out of bits. I'm careful to say run out of bits because in I2C land, a byte is 8 bits, but a message is 9 bits. And there's an extra bit that's added, which we'll talk about next. Let's finish this message. By closing this message off, we have something called a stop condition. In the English alphabet, we've already used S for start, so we use the letter P to indicate the stop. The stop condition is unique. It's the only time that clock is high and data goes from low to high. And that is a unique condition. If anyone on the bus sees that condition, they will stop what they're doing and they will know that the bus is no longer active and is not being used. Now we talk about that magic 9th bit, which is used to perform a handshake. And this is probably the single most important feature of the I2C bus system, because it means that for every 8 bits of data that you transmit, there is positive confirmation that it has been received at the other end. And the way this works is that at the end of 8 bits, the 9th clock pulse is used in the way like a parity bit to find out whether the device that received the data is happy. And if it is, then it will send back a 1 if it's an acknowledge. Excuse me, it will send back a 0 if it's an acknowledge. And if that device is missing from the bus or didn't receive the message or is busy and can't take the message at the moment, it will send back a NAC, which means the signal will be high. So for the observant person, if you take a device off of the bus because the bus is physically removed, say your device has modules and you take a module out, the processor that's talking to that device will get a NAC each time it tries to talk to it because the device is physically not there and the bus is pulled high by the resistors, so you will get a 1 signal back at the 9th clock period. And this, as I said, is probably the most single important feature of the I2C bus. It is also probably the biggest headache because it means that traffic on your bus is traveling 8 bits from master to slave, then 1 bit in the opposite direction, slave back to master. Which means that the information on the bus is constantly traveling back and forwards, and anything you put on the bus has to tolerate the fact that the direction is changed automatically. So some of you may be aware that there are buffer, repeater, or extender devices that can be used to extend a bus beyond its normal range. These devices have to be able to change direction without an external direction control pin. Okay. So what of all of this effort is the payload? And here's a little diagram that will show you that the message always have a start or a stop condition. The green arrows represent a start. The red represents a P condition or a stop. So we can say by observation this is a 2-byte message. So this is a case where the master transmitted an address, the slave acknowledged the address, and it transmitted a piece of data, and then it stopped because it had finished with the bus. So the first thing that happens is we send the address, which is 7 bits of data. Then we have to tell the slave device whether we are writing to it or reading from it. So the 8th bit of our 8-bit address payload is to tell it what type of signal, what direction it should go in. So in the red arrow, it's a write condition. In the green, it's a read condition. The slave responds. If the slave is present and recognizes its address, it sends back an acknowledge bit, which is the yellow arrows in the diagram. Now the master or slave can send data, which is the white or outlined arrow on the diagram. So we have sent several bits of information, several bytes worth of information, just to deliver 1 bit of data. So the payload on the I2C bus is inherently small. And now you can see why the subject of this presentation is, please make the bus go faster so I can get more payload, I can get more data to the destination in a given time. Finally, the slave sends the master an acknowledge if it received the data, or a not acknowledge if it did not receive the data. This is an accurate drawing of the I2C signal, clock and data, and it is drawn geometrically to represent the faster speed, the FM plus speed, which means that the clock can go up to 1 megahertz or 1,000 kilohertz. You'll notice that the clock signal is not nice square things that you saw in the textbook. They're more like shark's fins. And the reason for this is, on the way up, there is a natural CR time constant on the bus which changes the rate of charge as the signal goes up. And you'll notice when the signal comes down, it does it in a straight line, but it's not very fast. And this is all done by design. Because we want the bus to be wired or with resistor pull-ups, we end up with a sawtooth, a CR time constant, which is the one thing that the architect or board-level circuit designer has to grapple with. If you make the pull-up resistors too large, the capacitance on the bus will slow down the signal and you won't be able to get the throughput. On the other hand, if you make the pull-up resistors too small, your drivers won't have enough strength to pull the signal down to ground and you'll get data errors or you'll be susceptible to noise. So it's not in this presentation. If you want to know how to calculate the resistors, it's really simple math. I can show you afterwards, or I can email you some materials that will show you how to do that. The other thing that we see in the diagram is that we don't really have a lot of wait time. We have squeezed all of the dead time out of the spec to reach the 1,000 kilohertz clock speed. So we only have 50 nanoseconds of setup time between the edge of the clock and the preceding change in data. So we've probably maxed out what we can do with the I2C bus. 1 meg is probably the fastest we can go, unless we make some fundamental change to the bus. And when we do that, we lose backwards compatibility. We also lose some of the nice features of the bus, such as the wired or collision avoidance, and the fact that there's an acknowledge bit every 9th bit to confirm that the data has been received. Don't forget, this is all 1980s technology, and it's all 2 wires, 2 resistors. It's very unlikely we could simplify it. Here's an oscilloscope or MSO trace of a typical waveform, and you can see some features on it. The first one is you can identify the clock start condition because we see that the data line falls before the clock line. We can identify the end of the message because we see that the clock rises while data is low. And if you look at the bottom, you can see some funny stuff going on with those three levels. And that lower level is the stronger driver, which is probably the slave device, and the higher level is probably the driver. So you see a step in the waveform. Now, they still count as logic zeros. But when people look at these waveforms for the first time, they say, you know, that's odd. I'm expecting a binary signal. There must be something wrong with this part. Can someone help me? And it's just a case of education. They don't normally look at these signals. Now, you'll also see some spikes on the diagram. My pointer does not work on a TV screen, so I'll use my dirty fingernail. There's two spikes here. Those are caused by the bus changing direction. During the time that it changes direction, there's some uncertainty about the actual signal levels, which is why we built dead time into the spec originally. And these can be ignored for two reasons. Firstly, if they don't fall on a clock edge, no one knows about them. And the second thing is that in the FM Plus class of devices, we have a 50 nanosecond spike filter built into our silicon. So if there are narrow spikes on the bus, whether they're there deliberately or not, they will be ignored and not treated as signals. So I mentioned earlier that the bus is controlled by a bus master. So what exactly is that device? It's the device that starts the communication, and it provides the handshake as data is sent or received. So the master has to have the ability to transmit onto the bus and also receive. So a very simple beginner mistake is I connected my microcontroller GPIO to the bus and it doesn't work. And the reason might be that you use the tri-state or pull-up device on your microcontroller instead of an open drain or open, well, I doubt you'd get open collector on your microcontroller, but an open drain device. So if you're debugging hardware for the first time, that's one of the first things you might want to look for is whether the microcontroller has a tri-state or an open collector output device. And there should only be one bus master active at any time. The wording in this sentence is very carefully constructed to leave the door open. You can have more than one master if you wish. The bus has arbitration, which will allow two masters or more to coexist. Most of the applications are one master, many slaves, or one master, one slave. Built into the protocol spec is arbitration so that masters can decide who is going to take control of the bus at any time. This way it avoids collisions, which means that you have a very reliable and robust communication system. Once again, two wires, two resistors. So what are the slave devices? Well, this is the target of the communication. Either the master wants the slave to do something and sends it data, or the slave has data that the master wants to read. So slaves may provide data. For example, they may be a sensor, such as a temperature or thermal sensor. They may be external signals. They're reading push-button switches, reading from a memory device, or they may be some kind of customer configuration where you have switches on the board that you have to read periodically. Slaves may also take data from the bus. For example, they may be LED drivers, stepper motor drivers, general purpose I/O devices, or again, memory devices that you want to write to. Here is a page from the specification. This document is maintained by NXP Semiconductors. The patents on this technology have expired, so it's a bit of a free-for-all, but we notice that not only ourselves, but competitors refer back to this document when specifying their devices. What I want to draw your attention to is that on the right-hand column, there is a higher speed than the other two. This is our FM Plus product, and it has a maximum clock frequency of 1,000 kilobits or 1 megabit. So compared with the one in the middle, previous standard of 400 kilohertz, which is called fast mode, we have achieved a 250% increase in clock speed, which translates to a corresponding increase in throughput. If you would like a copy of the spec and you have a smartphone, you can scan my QR code, or you can ask for the document itself and then you can click on it. Here's a little table that shows the bus specs. The first one that's been revealed is called standard mode. This is the original spec, had a maximum clock frequency of 100 kilohertz. Notice also that the minimum clock frequency is 0. Why would that be? Think back to the application of the 1980s. If you're a TV set manufacturer and you're working with a remote control that does volume and channel change, it might be the length of a movie before someone presses a button. So the bus can go to an idle condition where there's no activity at all, nothing is lost, nothing is destroyed. The bus is essentially a DC connection with no activity on it. Our next step coming up is FM or fast mode. We maintain that DC ability. SM bus is derived from the I2C specification. It was written by Intel to meet some of their requirements. If you're a computer manufacturer or a CPU manufacturer with reference designs, what you really don't want is someone to unplug a peripheral and not tell you. If you unplug a battery pack, assuming it's powered some other way, or you unplug another device that's plugged in with I2C communication, you're in trouble because you could easily hang up the bus while the processor expects that device to respond. So in the SM bus, we don't allow 0. I think it is 10 kilohertz is the minimum clock speed. The next one, which we talked about today, is called Fast Mode Plus. And we have 1,000 kilohertz or 1 megahertz for the clock. You'll also notice that the 3 milliamp drivers have been boosted. We now have a 20 milliamp driver. Many manufacturers, including NXP, have stronger drivers than 20 milliamps. All we're saying is you need 20 milliamps to meet the spec and be interchangeable and compatible with other brands. Now, I left some space on the right-hand side of the slide, so I'm sure you're wondering what's going to come up. There is in the spec 2 other modes. They were put in before Fast Mode Plus, and they were in response to a particular customer requirement or market requirement to go much faster. These are called high-speed mode. Anyone in here heard of high-speed mode? Thank God no one put their hand. Oh, well, my boss did. But apart from that, no one else has probably heard of it. So there are companies that claim to have high-speed compatible peripheral devices that fit on the I2C bus. I don't think anyone's using them. So I put it on there for completeness. And if you are using it, please see me afterwards, because I'd like to have a chat with how you're doing that. Here is a handy tool that you can have to understand how the I2C bus works. It's available from NXP. It's also available from our distributors. This tool is meant for engineers, and we use it for 3 different applications. The first one is evaluation of hardware. So you can look at the hardware we're supplying, or that you can build your own hardware, or you can attach your own hardware to what we already have. The second one is to examine the devices. As we release new devices, we will be releasing add-ons to the software that supports this and also the hardware, so that when a new device is released, you can continue to use this basic product. And finally, our salespeople use it for tabletop demonstrations. They like blinky lights to draw attention, so we cater to that by showing them you can do that with I2C technology. What's inside the device itself? It has 2 I2C buses that have common ground and power supply, but they have separate signals. And there's a reason for that, which I will explain in a moment. Also on the bus are several devices. On the board is a 16-channel LED driver with the LEDs, and 2 GPIO devices, 1 on each bus. The rest of the stuff shown on the diagram are ports or connectors, which can be used for add-on boards later. Each port has both buses available to it. What drives those buses is the master. On the board is an NXP LPC microcontroller. It's the device that has USB on one side, so it can talk to a computer or the outside world, and it has I2C on the other side. As I mentioned earlier, to make the bus work, you need pull-up resistors. So we have provided pull-up resistors. There's actually a low, a medium, and a high-strength driver, so you can look at different bus time constants. And we live in a 3.3 and a 5-volt world, so with a jumper you can select which voltage you want on the bus. The second bus, the one shown in blue, is identical, except it is driven by an LPC Espresso module. And you may have seen those if you're familiar with the NXP product line. We have some little plug-in boards that have a programmer built in. You can write your own code, plug it into our board, and drive the other bus. We also have in our product line bus controllers. The idea of these is very simple. You take a microcontroller that speaks parallel port signals, and you let this chip do the heavy lifting of creating the clock and timing for the I2C bus. By using this device, your processor, or whatever it is you're using that wants to drive the bus, doesn't have to understand the timing or the signal format for I2C. We do it for you. This is a screenshot of the graphical user interface, or GUI, which NXP supplies for free to support the board I've just described. And lo and behold, there's that diagram again. So we're just showing the version number here, which is the current one. When the hardware is connected, we get a confirmation signal at the bottom. And we also have a way to change the clock frequency on the bus. So if you have a design that you're currently using at, say, 100 kilohertz or 400 kilohertz, and you would like to know what happens if you increase the clock beyond that, you can go ahead and program the clock generator on the board to generate the new clock format up to 1000 kilohertz. Here's a photograph of the main board that is in the box. I'm just going to show you the floor plan. Here's the stuff for bus 1. Here's the stuff for bus 2. Here's where the power and USB comes in, and you'll also notice there's a chip in there. That's the LPC that acts as the MCU master controller for bus number 1. I mentioned earlier you need pull-up resistors. We give you a choice of low, medium, and high pull-up resistors. We give you a choice of 3.3 or 5-volt pull-up. To accomplish all of that, we have a field of little connectors. Put jumpers on them to program them the way you want. We have 2 GPIO devices, one on each bus, and they can connect to external devices using the connectors at the far right-hand side. I also mentioned we have a 16-channel LED driver. This is an NXP product. If you know about driving LEDs, you usually expect to see a resistor associated with the LED. This device is a constant current driver, does not need the external resistors, so the layout around here is quite clean. There's no parts on, no sleight of hand, there's no parts on the back of the board. The device directly drives the LEDs. We have 4 white LEDs, and we have 4 clusters of RGB, 16 channels total. When you use that chip, you have to decide what the maximum current will be through your LEDs. That's a hardware consideration. So on our demo board, we use the rheostat or potentiometer, so you can adjust it. You can run 20 milliamps through the LEDs all day long, you won't damage them. But the part itself will provide up to 57 milliamps per channel of drive current. So move that screwdriver with caution. Okay. Finally, there's a little scratch pad area on there which allows you to plug in your own components, solder your own components. Some of our products are in fact, nearly all of our products are in surface mount packages these days. So we have a range of breakout boards that allow you to attach our part to a PC board, breaks it out to a 0.1 grid, which fits onto this board. So if you have a device from us, or, and you didn't hear me say this, if you have a competitor device, you want to see how well it works, you can go ahead and solder it on our board. Finally, we have a couple of utilities. There's sort of a little logic probe down here. It's an LED with a FET isolator so that you can probe a signal and find out whether it's logic 1 or logic 0 and not have to haul some lab equipment in or wire up something else to find out the voltage level. And finally, as I mentioned earlier, on the right-hand side, GPIO outputs. They have 10 pins, 8 channels, power and a ground, so you can connect all the hardware there. In the kit, we have a strip PC board that has 8 switches and 8 LEDs on it. So you can then plug those together with the supplied ribbon cables. As you can see, there's several connectors around the board. Anything that's port followed by a letter is a place where you can plug in a daughter card, either a current one or a future one, which allow you to work with current devices and keep this kit current. We also have 2 tester ports. I discovered, and they're here somewhere around here advertising, there's a company in Silicon Valley that makes a really nice I2C protocol analyzer and data logger. The name is Total Phase. They don't give me any money or any kudos for saying that, but I love them so much that I put their connectors on the board so you can plug them straight in. Here's the LEDs. Here is the mysterious socket in the middle that did not have a shroud around it. Plugged in there is a bus buffer board. This is a way to link bus 1 and bus 2 together by passing the signal through a bus buffer. The reason the socket doesn't have a shroud is you can unplug that board and rotate it 180 degrees if for some reason you wanted the signals to flow through the device in the opposite direction. The devices that are on this board are our latest bus buffer devices, and they're capable of working down to 1 volt on one side, 3 to 5 volts on the other side. So to generate that 1 volt, we have an onboard LDO and a potentiometer. So you can tune the board for your particular system voltage. There's some places up here where you can change the loading on the 1 volt bus, and there's lots of test points so you can connect up signal monitoring equipment such as an MSO, and you can look at the signals in their 1 volt variety or their 3.3 volt variety. Here are the fingerboards I told you about, and this is a daughter card plugged into one of these accessory sockets. It has a 16-channel GPIO on it. To cover 16 channels, we needed 2 of the 8-pin boards, and they're bundled in the box. If you'd like to know more about it, this will take you to the landing page on the corporate website. And if you want your own kit, scan that and see what happens. I'll talk a little bit about the devices. The one that's on the card, which is our LED driver, is the PCA 9955 device. And here is a block diagram of what's inside the chip. We won't go through it in much detail. I just wanted to show off how complicated that part is. Here's the challenge. To make the first LED light up, you need to send it 55 bytes of configuration data. So there's a challenge, just getting, someone sent 54 bytes and wonder what happened. Yeah, it's a challenge to get this to light up because there are so many programmable variables inside the chip, you have to have the full suite before anything will happen. Here's an application circuit. It's almost what's on the demo board. We have a master sending I2C signals to the device itself. We have an external resistor. I mentioned it's a potentiometer, so you can adjust it on the hardware demo board. And we have some LEDs. In this particular diagram, the LEDs are shown as chains of individual diodes. And the reason for that is this device can handle up to 40 volts on the I/O side. So this is perfect for those large arrays where you have multiple LEDs to light something up. You can put chains of LEDs and go up to 40 volts. On the demo board, it runs from 5 volts, 1 LED. Here's the buffer device. The block diagram for this is remarkably simple. All it consists of is buffer amplifiers that buffer the signal from one side to the other. It gets a little bit more complicated because we have to have bidirectional capability. So we have buffers facing in either direction, and we have an enable pin so you can isolate a section of the bus by turning off the enable pin and disconnecting those drivers. It's not in today's presentation, but there are some tricks to make these work. To make them work well is the reason for the 3-level signal. Because if a signal is passed through this path, it is also reflected in this path, and you end up with a race condition where they lock up. Both buffers will turn on. The only way to turn them off is to cycle the power. So we design them in a way that when you're going in this direction, the signal coming out here is okay for the load, but is ignored by the device going in the other direction. And that's the reason for the little step in the logic 0. We call it bus buffer offset. Here's an application circuit. In this case, we're going from the world of 3.3 volts to 1.2 volts. So the bus buffer itself has 2 power supply pins. One of them is used for the chip itself and one side. And typically, the higher voltage side powers the circuitry in the chip. So it's hard to make these devices work from 1.2 volts only. On the 1.2 volt side, we have another bus, which is isolated from the first one and has its own pull-up resistors. On the other side, we have a similar bus with its own isolated drivers, so it's pulled up to the different voltage. So what we've effectively done is cut our bus into 2. Logically, it's one bus. The signals pass from one side to the other, but they operate at different supply voltages. Finally, we have the GPIO expander. Compared with the other 2 I've shown you, this is sort of a medium complexity device. The important thing is that there's an I/O port that has 0 through 7, 8 channels. And we have on this side the I2C signals that are used to connect it to the bus. The device has address pins, so you can have multiple of these on the same bus and talk to them individually without conflict. Here's an application circuit for it. The processor is driving the I2C bus. The other side of the GPIO is driving something. We don't know what it is. It's entirely up to the application how you use it. For example, P7 is an output. It's used to turn on an indicator LED or some other functional LED. These other ones up the top here, 0 and 1, are actually inputs. They're receiving digital signals from somewhere else in the system, and this device is acting as a translator between the binary world and the I2C bus world. Notice that there's only a few pins on this side and a lot of pins on the other side. The main goal of the GPIO is to reduce pin count on the processor. Not shown on the previous diagram, here's a temperature sensor. And this is an example of a device that generates data. Using ambient temperature and a band gap temperature sensor, we get an analog signal proportional to temperature. We convert that to a digital signal using an onboard A to D converter. The device has an onboard clock, which is unusual for a slave device. Normally, they don't have any clock on board. Then on this side, we have a number of watchdog devices. We have internal registers that can be used for upper and lower temperature sensing. And there's also a hardware path that if there is an over-temperature condition, which is so severe that it stops your processor from working and the I2C bus is no longer working, we can control some piece of hardware, such as shut down the power supply, turn on the fan, do both, cause an alarm. And then, of course, we have the I2C signals. We have 3 address pins, which means that you can have 8 independent temperature sensors connected on the same bus. And here's an application circuit for it. We have the I2C bus talking to the device. We have the address pins. In this case, we're showing that they can be dynamically changed during the life product or while the product is running. And we're using that output device as basically a temperature alarm to indicate something has gone wrong and a piece of hardware has to take care of it. All right, so summary. The established I2T technology has a long track record. The latest improvements from NXP are called FM Plus or Fast Mode Plus, and they will give you a 250% increase in clock speed, which corresponds to an increase in throughput on the bus itself. The new devices from NXP are branded FM Plus. They are different from the existing devices because they have stronger drivers and they have faster clock speeds. We have support tools, which includes the FM Plus development kit that I talked about, and a software tool that runs on a PC and connects to it to control the devices that are on the card.